Okay, we are live. Okay, good. 那么我知道了。Now I know that I have voice. Okay, I'm going to try English in this live streaming, but yeah, maybe I will have some start or inconsistency in my speaking, but yeah, you should forgive me. It's my first time live streaming in English, but I think it will get better if I practice more. Okay, let's see how the recent updated papers on machine learning calibrations for excited state calculations. Okay. Why should I want to do excited state simulations? Interaction with light. It could be interesting. Okay, so first I will add every updated papers into my Zotero library, and then I will add tags for them in the Zotero. So this live streaming will be divided into two parts. First, I will add papers into the Zotero, and then I will give tags to them. Yeah, that's a plan. Okay, good. It looks like this is a really long paper. That's why it takes a while. From Condon, molecular absorption interference. Okay, I think this paper is related to the computational spectroscopy. And what kind of spectra did they calculate? Molecular absorption and emission spectra. Okay, so I'm kind of interested in everything related to the computational methods. So I want to know what computational methods can do and what it can calculate. Okay, computational screening. Okay, it's computational screening. So I think it's the showing force of how many computational resources they have, because usually computational screening is really computationally intensive, computationally time consuming, I think, or resources consuming. Okay, now nobody is here, but yeah, it's fine. It will get there. Single entity nanocatalysis, carbon nanotubes, and okay, so this one on the oxidation and reduction. How did this process happen? Why do we want to study this one? These are the questions that I'm very intrinsic density functional errors. Okay, we are using VASP. Here is different things. Okay, they are using different exchange correlation functionals to calculate here and okay, so I think they're focusing on the different computational schemes on the results. Yeah. Simulation nanoparticles. Simulations of the electrochemical oxidation of platinum nanoparticles on various shapes. So I think in here they are using maybe molecular dynamics. I'm not so sure. The procedure is referred to GREG. Grand canonical simulation approach using relative force fields. Okay. Relative force fields. It's really hard force fields to parameterize. Okay, absorption and reaction. Yeah. STM study. Okay, so why do we need the STM study? What can STM tell us? It can tell us the structure, right? But if we know the structure, what can we learn from it? We can know that, okay, what kind of where is the active site? We can know there. For example, if it's a step surface, then we know that maybe in the step is the active site. I think that is important. Substrate roughness. Lead-free alloy double peroxides. Okay, still right now people are studying perovskites. Okay, it's a really hard word to pronounce. Lead-free or inorganic alloyed double perovskites. Okay. What is double perovskites? It's just two things. One is this, another one is this. And how did they connect it with each other? Yeah. Sorry, I'm not so sure about this. Delay thermal relaxation in lateral heterogeneous transcendental. I think this one could be related to the molecular dynamics simulations because it's thermal relaxation, so we know that if we elevate the temperature, we can study how does the morphology or the structure of this transition metal dicharcogenize. Yeah, I don't know why it's spelled like whether my pronunciation is correct or not. Okay, design principles for metastable standing molecules. Metastable functional molecular structures. Okay, so on surface it will form some metastable states, and those metastable states could have some really interesting properties. That properties will be used to further applications. Oh, to be honest, I think speaking English is quite different than speaking Chinese. Yeah, I think because I write in English, all my note taking is in English, so I think in this way I can think more clearly about what I'm trying to say. But sometimes, yes, sometimes I still need to think about it. I cannot speak as a native speaker because, they have been speaking for like 20, 30 years. Right. But yeah, I'm getting there. I'm getting better and better. Okay, simulations of structure and morphology influence of size and composition on the transformation mechanics. Okay, I think they studied the structure transformation of a nanoparticle, which is quite interesting. So we would like to see what kind of external environment or environmental conditions, what kind of temperature, pressure, pH, or maybe chemical potential of certain ions could impact this. And I think they're using combining atomistic simulations and electronic structure calculations. Okay, electronic structure calculations. So that means they're using DFT or NAB and EB simulations. Computational details. Okay, let's see. Okay, so one is cube octahedral. This one is cube octahedral, and this is icosahedral. There are two different force field calculations, which means they're using molecular dynamics. They're using EAM potentials. EAM potential, I think it's a semi-empirical potential, which is really fast, but its accuracy is not as good as, for example, the functional theory or other stuff. DFT simulations using quantum espresso, PBE. Okay, cool. Okay, first they're using EM, then use PBE D3 and also PBE D3. Yeah, we can see here that there are huge difference between the results from EM and PBE D3. So that means that, but the difference between PBE D3 and PBE D3 plus, I think, Plaso, I'm not sure whether it's kind of a correction, right? I assume. So we can see that the difference between whether or not we should incorporate corrections are similar. But the difference between EAM and PBE is quite different. So this means that the EAM potential may not be suitable for this case. I forgot whether I have added influence of size. Yes, I have already added. So let's move on. Silicon cluster with Okay, I think it's about 2D material. The hexagonal boron nitride. Boron nitride is kind of the isoelectronic. Isoelectronicity. Okay, isoelectronic. Okay, it's isoelectronic to graphene, which is like similar. Which could have similar like electronic structures, and could also have some similar mechanical structures or thermal structures, conductivities, yeah, something like that. Okay, ultra fast photo carrier, exploring critical synthetic parameters. Okay. This one is different magnetic phases, different structures on the magnetic properties. The think magnetic properties is still missing in chemistry, but I have heard one article about the combining magnetic properties into density functional theory, and there are some tools I think available that you can add the external magnetic field into your simulations. Reticular nanoscience. Reticular nanoscience. Okay. Bottom-up assembly. Nanotechnology. I think it's a new concept. The chemistry of metal organic and covalent organic frameworks. Okay, MOF and COF. Most diverse and elusive among the chemical science. It can be radically expanded, blended with nanotechnology. Okay. Cool. You know, chemical science is really vast. So I think chemistry is kind of a toolbox where, to be honest, you don't really need to understand how tools works, right? Because physics is all about understanding what's going on, about what's going on in the process, what kind of concepts do we use to describe it, what kind of mathematical formulations we need to write down and solve them in order to predict or understand what will happen. So that's why we have some fundamental laws about maybe like Newtonian mechanics or classical mechanics like Lagrangian or Hamiltonian, something like that. Then we have electrodynamics, we have statistical mechanics and quantum mechanics. Yeah, something like that. They're quite... But chemistry, I think it's about tools that if you want certain properties, what kind of chemical system you can have in order to meet those needs. And those chemical systems, are they stable enough? Can they be easily synthesized? Are they cheap? Yeah, I think those things are very important. Okay, let me go on. Okay, I think this is a computational study, and they change different content of lithium doping. I'm not sure how does the lithium doping. Okay, so you can see that there's an inverse trend between the, I don't know, this one is conductivity maybe, and this one is the activation barrier of the lithium, I believe. You can see that when it has higher activation energy, it's lower conductivity. Yeah. Yeah, I think for chemistry right now, for one system, you have many different methods, different level of methods that you can use to describe. First, if we want really high accuracy, you need to use some quantum chemistry method like Hartree-Fock or like couple cluster methods. But if you want to go, okay, I want some efficiency in there, you can go density functional theory, but there are different levels of density functional theory. For example, we have LDA, local density approximation. We have GGA, gradient, a general gradient approximation, which also consider the gradient of the electronic density. And then we have matter GDA, where we incorporate the second order derivative of the electronic density. But then we have hybrid function, which we incorporate like exact exchange. For example, we add a certain ratio of exact exchange from Hartree-Fock to there. For example, HSE of 6 or PBE 0. There are different kind of level of theories, and it can go up. It's called the Jacob ladder. And then going up, you have molecular dynamics. You have first principle ab initio molecular dynamics, where you use density function of theory to calculate the force or the interaction potential between atoms, and that is really accurate, but it's very time consuming. And then you have like force field, but now you have like machine learning potential that can be used as a surrogate model for the density function of theory, and you apply to molecular dynamics, then you can simulate like larger systems and longer trajectories, and you will get more reasonable statistical sampling. Yeah, like this. Okay. Yeah. Because I left this one for like 2 or 3 days, then you can say it's already like 200 more papers, which you can say there's a really live field of chemical research and different aspects. Some experimental stuff, some theoretical stuff. Okay, so I think for now I need to only focus on theoretical work, because experimental work is interesting, but I think looking at theoretical work is like more interesting stuff for me. Formic acid and the application of in situ hydrogenation. Boostings. Regulating interfering. I think this one is correlated to with the physics, the Hall effect. Reorganization energy of electron transfer. Okay, this is very interesting. The intrinsic fragility of liquid vapor interface. Liquid vapor interface. Microscopic simulations of electrochemical double layer capacitors. In the context of blue energy harvesting and desalination, predict power of simulations in particular for future devices with complex electrode. Okay, I think for chemistry or computational chemistry, there is a really huge mistake. Is the misfit between simulation computational methods and experimental results. Because when you do an experiment, there are so many different factors that can have influence on the results. Then as theoretician, I think the goal is like when you only try one factor and it's trying to face the experimental results, you can say that, okay, so this factor determines that experimental results, right? But what about other effects? Can they have similar trends? Then how do you determine which one is the most like influential factors? You need a formulation to really determine, okay, which term has the largest number that I can say, okay, this effect has the largest impact. But I think for theoretical work, what we can do is we can only like determine what kind of factors can impact the results. We cannot say, okay, the results is coming from this factor alone, because there are so many different factors and we are not as one-to-one map in, like, for example, mathematics. In mathematics, you have a certain conditions that you need to meet in order to get a theorem or a conjecture or something. You need to have those conditions in order to constrain that. But in chemistry or even in biology or social science, there are too many different variables available, so that it is really hard to determine which one is the most important determining factors. Study the impact of pre-exponential factor. Okay, how did they get the pre-exponential factor? Using Arrhenius equation? Or it has another way? Nucleation mechanism in nickel. So I think in chemistry we didn't looking for causality, we're looking for causality, we're looking for correlations. So whether or not two variables has correlations, maybe we can formulate a way to say that, okay, how does this variable affect the overall phenomenon? We can find a narrative to do that. But if we change this variable, can we actually change the output? The answer is not actually, because we don't know whether if we change this variable, it can cause maybe a second order effect or third order effect, and those things can also determine the final outcome. So I think that's is what we need to think about. Mhm.